Previously, given a holomorphic map phi from a compact Riemann surface X to the projective space, we have associated to phi a collection of divisors, which we'll denote by this. Right? So what is this collection of divisors? Well, we're just pulling back the hyperplane divisors of Pn, hyperplanes of Pn. For example, if X already lies in Pn, and this is just an inclusion of a subcomplex manifold, then we can see in this picture the collection of divisors here. So if H here is a hyperplane in Pn, then this pullback of H is just going to be this green curve. Our next question, naturally, will be which collection of divisors arise this way? The answer is that this is a base point free linear system, and all base point free linear systems arise this way. So this will give us a bijective correspondence between holomorphic maps from X to projective space up to coordinate change and base point free linear systems. This allows us then to think of maps to projective space as base point free linear systems interchangeably. So let us first explain why this is a linear system. Right, which linear system does this correspond to? Because it would have to correspond to some subspace of some LD for some divisor D, right? And the divisor D is gonna come from the tuple Fi. So every holomorphic map phi correspond to some tuples of meromorphic functions on X, right? So the divisor D, we can get this from tuple Fi, and the linear system here will correspond to the span of Fi, which is a linear subspace of LD. To build some intuition for this, let's first do some concrete computation. And for that, let's review quickly what the definition of this pullback divisor is. So a hyperplane is always cut out by some linear form, L. So the pullback of this hyperplane is the pullback of this divisor of this form L, which I should now define. Because you are probably only familiar with divisors of functions, right? But this is a form. So what does this mean? Well, here L is homogeneous of the degree 1, and there's nothing special about degree 1, so we'll define this pullback of div f for any f homogeneous of degree d in general. So this phi star, this pullback of div f, is a divisor on X. And to define a divisor on X, it's equivalent to just define its value at every point P on X, right? So what is this value at a random point P? Naturally, you might think, oh, we should define this to be order of vanishing at phi p of f. But the question here is, f is not a function on Pn, right? It's just a form. But no problem, we can actually resolve this pretty simply. So phi p is gonna lie inside some affine p's, right? And so, for example, let's say phi p lie inside x naught not equals to 0. Then we can, instead of f, we can look at the affine restriction of f. In a sense, this is the same as looking at the order of vanishing at phi p of f divided by x naught to the d. And more generally, we can just define this to be the order of vanishing at gp of f over g, for we can choose any g such that degree of g is equal to degree of f, so that this becomes a function, and that g doesn't vanish at phi p, so that this doesn't introduce any extra pole. Alright, so now let's look at some concrete examples. Let's say we have a map phi, holomorphic map from X to P2, and we have a point P in X, right? We want to compute the divisor phi star div xi by computing its value at each such point P. Now let's take some local coordinate z centered at P, and then in that local coordinate we can always write phi as this form, so some powers of z and then multiply with a unit in the local ring at P. So what we mean is that this ui, z, they have no poles or zeros at P. Since we only care about the order of vanishing at P anyway, so let me just erase all of this ui. They don't really matter. Now, let's look at the first example. So to find the value of phi at P, remember we choose a different representative of this map. We divide all of the coefficient by z to the minimum order of vanishing of these coefficients at P. So we divide everything by z squared and get the following. Right? And so we see that phi P is gonna be 1, 0, 0. Thus, in this case, we see that the point Vp is gonna lie in the affine piece x0 not equals to 0. Thus, for example, if we want to compute the value of the divisor, the pullback divisor of x1 at p, then we would just take the order of vanishing of x1 divided by x0, and then that's going to be the same at the order of vanishing at p of this coefficient z over 1, right? So it's going to be 1. Similarly, if we change this to x2, then here we want to look at the order of vanishing of x2 over x0 at Vp, right? And that will just be the order of vanishing at p at z to the 4th over 1, so that's going to be 4. Now, to check if you understand, let's look at the second example. We have this here, and then to evaluate this at p, we are gonna divide everything by z to the minus 5, because the smallest order of vanishing at p here is minus 5. So we'll get this. Now, could you tell me quickly, what is this and this? If you understood the previous example, then you will see very quickly that this has to be 3, corresponding to the 3 here. And then this one has to be 6, corresponding to the 6 here. Now, if we call the original components function of phi, f0, f1, f2, we want to express this in terms of the order of vanishing at p of this fi. So what's the relationship? So how did we get this exponent 3? Well, we got that by actually dividing this by z to the minus 5, right? So if we define dp to be negative of the minimum order of vanishing at p of the fi, so in this case, it's going to be 5 because the minimum order of vanishing of the fi is minus 5. Then we see that this here, this value at p, is just going to be the order of vanishing at p of f0 plus dp. Right? Order of vanishing at p of f0 is minus 2 plus dp is plus 5. Now that gives us this 3. Because the point is that this here is going to correspond to this power over z here after we have chosen a good representative. But we got this good representative by dividing each of the fi by z to the power, by dividing this z to the power of minimum order of vanishing at p of fi. So in other words, we can also think of it as multiplying each of these fi by z to the dp. So to get this power, we're just gonna add the order of vanishing at p of each fi with this dp. So now, if we patch together this local information, if we define a divisor d this way, so that at every point p it's going to be equal to this, then we got a divisor d which we call the GCD of div fi. And this local equality gives us a global equality, so we see that the pullback of the divisor x0 is just going to be div f0 plus d. And observe that it's going to be non-negative. Why is that? Because, for example, at this point p here, what is this value here? This value here is just this 3. So we have chosen the d so that this is gonna be positive. Basically, we've chosen the d so that this is just gonna be the power of z after we have chosen a good representation. In a good representation, none of this power can be negative. And this is true for every point p, so together we get globally that this is an effective divisor. More generally, if we take any hyperplane in Pn, then the hyperplane must be of this form. It must be a linear combination of xi. So its pullback is just going to be div of a linear combination of fi plus d. And this is, again, an effective divisor. And it's linearly equivalent to d because it's different from d by divisor of a function. So this is actually inside this complete linear system, right? And we see here, observe here, that this is just a linear system, and it corresponds to the span of fn, right, inside LD. So to sum up, given a holomorphic map phi from a compact remote surface X to the projective space, we can associate to it a linear system as follows. So if we take D to be the GCD of the div fi, then we can associate to it the map phi, the complete linear system corresponding to the span of fi inside LD. Divisors in this linear systems are just gonna be of the form div g plus d, where g is in this span of the fi. We can also go in the other direction. So given a linear system Q, corresponding to a vector subspace of LD, we can take a basis of this vector subspace, and then that will give us a tuples, which again will correspond to a holomorphic map from X to some projective space. However, note that this doesn't work for just any linear system. We have to choose a base point free linear system. And so we'll explain what that means in the next video.